Hey guys, my name is Sartek Kamboj, and in this video, as you can see by the screen, we're going to learn about merge sort, which is a really popular sorting algorithm that teaches you an important paradigm called divide and conquer. So without further ado, let's just get right into it. So as I already said, we're going to learn about merge sort, and by definition, merge sort is a computationally efficient sorting algorithm known for its divide and conquer strategy. And in a moment, we'll be going through an example to see exactly what that means and understand how that plays in a real array or when you're sorting real numbers. It was developed by John von Neumann in 1949, so it's pretty old and it's tested the strength of time. So we know that this algorithm is pretty good, and we'll see why in a second. So instead of just explaining what the rules of the merge sort algorithm is, instead I think it's better to see an example, because if you just kind of describe what the patterns are or what the steps are, it can get a little confusing, but it makes a lot more sense when we're talking about an example or when you see it in action with a real data set. So as you can see over here, we have an array with the numbers 7, 5, 0, 2, 1, and 4. So clearly they're unsorted, and note that there aren't any duplicates in this example, so we just won't be handling for that right now. So the first step in merge sort is that at every iteration, you break the array in half. So essentially over here, we start off with this entire array, this one large array, and then we break it up into two arrays. So we have 7, 5, 0 here, and 2, 1, 4 over here. And what we do is that we stay on one side the whole time and just keep breaking down the array until we get into single units. So as we see over here, we break down 7, 5, 0 into 7 and 5 and 0, right? Because it's about the halfway point. Then we break down 7 and 5 into 7 and 5. Or we break down the array of 7 and 5 into two separate arrays that contain the numbers 7 and 5. And the important thing to know here is that although I showed these processes happening at the same time, not oftentimes, what actually happens is that we break the array, and then we stay on one side until we've completely broken up the entire array, and we come back to this original version of the array. That might not make much sense right now, but as we continue, it'll make more sense. So right now at this stage, what we have is that we have all our arrays. Our array has been broken up into individual arrays with only one element each. And so up to this point, one thing that you probably noticed, all we're doing is just breaking down the array. We haven't started sorting. And you'll see in a second, by definition, merge sort sorts when you're merging arrays together. So when you're breaking the arrays down, there's no sorting happening. But when you put it back together, you start sorting, and you'll see how that works. So now, as you can see, we have broken the array into single units. And what we do is we create another array called temp. We'll call this array temp. And this is the size of the original array. Notice how there's 6 elements here, and temp has 6 empty elements itself. And the reason why we do this is because we want to copy the elements into temp. And when we copy it into the temp array, we make sure that it's sorted properly. So over here, we start off from the left, because remember I said you break it down and you keep going down the left side, and then you come back up, and then you go down the right side. So over here, we're starting off at the left. We sort the individual elements with 7 and 5. And so we get that we copy 5 in first and then 7, right? Because obviously 5 is smaller than 7. And what we do is we take these two indices and we copy it over here. So contrary to what this diagram is showing, first what we do is we sort them, we copy them into temp, and then we put them back into the original array in a sorted fashion. So what this does is that once we deal with larger numbers, we avoid the complexity of having to manage which number is where. Instead, we're just sorting the numbers into an empty array, and then we're copying those numbers in that sorted fashion back into the original array. So as we can see over here, so now we have 5 and 7 in a sorted fashion. And what we need to do is we need to take this 0 and we need to merge it with this array of 5 and 7. So once we come into this step, obviously 0 is less than 5 and 7, so it goes in the front. And so what we do is we take that 0, we put it in the front, and then we put 5 and we put 7, and then we copy the numbers in that order back into the original array. So now you can see that the first half of the array is already sorted. And notice how we haven't touched this at all, right? We're still on the left side and we're just making our way up until we get back into a stage or a situation where the left side of the array is completely sorted. So now the left side of the array is completely sorted, and the next step we'll be moving on to the right side. So this is sorted. On the right side, we start off, if you remember over here, we have the numbers 2 and 1. And so we need to sort that, and we get that obviously 1 is less than 2. So we copy those numbers into temp array, placing 1, then placing 2, and copying that back into the original array. And the important thing here is to know is that we haven't resorted temp yet, right? All we've done is we've just replaced, we've replaced it so that the right side of the temp array corresponds with the right side of the unsorted original array. And we'll see at the end, when we merge everything together, is when the entire array becomes sorted. So obviously right now we have the numbers 1 and 2 in order. The last element is empty, and so what we do is we take the last element on the right side of the original array that hasn't been merged yet, we merge it with this array, and we get the numbers 1, 2, and 4, right? We put that into temp, and then we copy those numbers back into the original array. So at this point, we can see that the left side of the array is sorted, and the right side of the array is sorted. So this is kind of an important concept to know, is that what we're doing is at each step, we're having one side that is sorted and the other side that's sorted, and we can kind of mix and match them, so we get an entire array or a combined array that's also sorted, and it just makes the sorting process much faster. And we'll talk about how time complexity and space complexity kind of comes into play here, and then in the next few slides. But that's just an important thing. So we're dividing the array in half and then conquering that part of the array. So that's where the term divide and conquer comes from. And so the last step is merging this array, this part of the array, with this part of the array. So obviously when we do that, we get 0, 1, 2, 4, 5, and 7, right? We copy those values into the temp array, and then we recopy those values into the original array. So we finally get an array that is completely sorted. So the main takeaways from this algorithm is that the actual sorting occurs at the lowest levels when items are being copied into the temp array. So when we're merging arrays together is when the sorting is happening, and we copy them into the temp array and then copy them back into the original array is when we kind of get the actual sorting, hence the name merge sort. The time complexity of this algorithm is n log n, and for those of you who don't know, time complexity is basically kind of analysis and like a worst case scenario, how long this algorithm is going to take with respect to the number of elements in the input. So if we go back, the reason why it's n log n is because at every situation, notice how we're dividing it by 2. We're dividing the array by 2, and because of that, we know that the time complexity there is log n. And what's happening at every level, right? At every level, we're sorting n elements. The entire array is being sorted in some fashion, right? So over here, at some point, all these numbers will be sorted. Then in the next level, all of these numbers will be sorted. At every level, numbers are being sorted, and the entire input array is being sorted and copied in a temp array. So we can see that every step, there's log n steps, and at each step, we're sorting n elements. So that's why you multiply n times log n, and you get a time complexity of n log n. And then over here, we can see that the space complexity of the algorithm is O of n, which is because we're creating a new temp array that has n input elements or n input spaces. And so the reason why we say it's n is because the original array has n elements, and this new temp array that we've created during the process of the algorithm also has n elements. Therefore, the space complexity is n. And so hopefully that makes sense. One last thing that we're going to do is we're going to go through a merge sort simulator to kind of understand this algorithm a little bit more. And so if we click on the link, we can see we'll start off with an array size of 6 because the concepts stay the same and there's just less steps to go through. And so over here, we see that the original array has 992, 955, 714, 655, 586, and 259. So actually, if you can see, this array is not only unsorted, it's actually sorted in a reverse manner. So this is probably the worst case scenario your algorithm could get, because literally nothing is sorted and it can't rely on any kind of consecutive numbers that are in sorted order in order to kind of optimize the algorithm. So this will really give us like a strong understanding of how long the algorithm takes and how it works in a worst case scenario. And so we can see over here, you have the entire array. They've broken up the array into two parts, right? You have 992, 955, 714, and then you have 655, 586, 259. And you always select this left subarray. You work down the left side, and then you work down the right side. So as we can see over here, they once again break it up. So you get 992, 955, and then 714. And so this is the example I was talking about before, where you only work on the left side first, and you forget about the right side. So we continue. You select the left subarray, and then you break it down even further. So you get 992 and 955. And notice how both these elements can't be broken down any further because they're arrays of single elements. They only have one element in them. So this is where the merging happens. So imagine that this is temp. It might be a little confusing, but generally this is another separate array that we're copying elements into. So we're sorting it, and obviously 955 comes in first, then 992. And then we move to the right side of the array. And so notice how over here, this part of the array is sorted. It's 955, then 992. Obviously, before it wasn't. And now that we move to the right side of that subarray, we can see that there's no elements. There's only one element in that array. Therefore, it's broken up into its smallest part. And so we can see over here that now we're merging these two arrays together. And so 714 comes first, then 955, then 992. And so we can already see by this algorithm that just by breaking down and combining and merging arrays together, we very quickly have a sorted part of the array. And now because we're done with the left subarray, now we're going to move on to the right subarray. And so we can see over here that they break this array into 655 and 586. And then the other part of the array has 259. And now we stick to the left side of that subarray. And so we break it down into 655, 586, and then just copy those elements in a sorted manner. And then we move on to the right side of the array. Obviously, this is pretty repetitive, but we move on to the right side of the array, and we copy elements back by merging them together. And so we can see that now we have two sorted arrays right here. And so the important thing to know is that now this part of the array corresponds to this half of the original array, and this part of the array corresponds to this half of the original array. And so obviously it's very clear that these aren't sorted. If you were to just put them together, they wouldn't be sorted arrays. But when we merge them together, we'll be able to sort them pretty quickly. And so now we copy elements back, and we can see that 259 comes, then 586 and 655, then obviously the other parts of the array. And so what this does is really optimizes the sorting algorithm, and it makes sure that we're not constantly like going through every element and then going through every element beyond that over and over again. And so hopefully that helps. Hopefully my example and the visualization here helped you understand that a little better. If you have any questions, leave in the comments. Other than that, thank you for watching, and bye.